If you have ever had to deal with a sudden tear blockage or unexpected gun plugging while running high calcium coals, you know that the chemistry of your ash is not just a lab report. It's a matter of operational survival. So today we are performing a thermodynamic autopsy of high calcium bituminous coal to master the chemical levers required for optimization as fusion. So by the end of this session, you will gain three specific technical deliverables. First, a microscopic understanding of the sintering glue mechanism. Second, the ability to predict slagging onset using the liquid phase activation curve. And third, a strategic playbook for blending that effectively. So on the screen, you see a slick, dark schematic of a blast furnace tuer highlighted with a orange digital blueprint. It represents the diagnostic precision we need. We are not just looking at coal, we are looking at the molecular warfare inside your raceway. To understand the war, we first have to understand the paradoxical nature of our primary fuel source. And our uh, as you can see, there's in the industry we often talk about the Sendog paradox. So on the left, in the emerald green box, you see the incentive. This high calcium bituminous coal is a high value fuel because it offers exceptional combustion stability and incredibly low sulfur down to 0.21%. So that is a massive operational win for the hot metal quality. However, look at the neon coral box on the right. The fiction, the ash fusion temperature dropped dangerously low with a deformation temperature of 1465 Kelvin. The so what factor here is immediate. While you are saving money on the fuel cost and sulfur removal, you are risking severe slagging, corrosion, and catastrophic PCI gun plugging. We rely on PCI to replace expensive coke, but if you don't uncover the precise mechanism causing this low temperature slagging, our cost saving measure will be erased by the furnace downtime and maintenance expenses. So we have to identify that mechanism by literally watching the ash die and the reform under a microscopic autopsy. So now it is a turn to track those autopsy. So let's look at the physical evidence. On your screen is a four-stage visual progression of a ash sintering from 873 Kelvin to 1473 Kelvin. So notice the first three slides, the ash remains a loose, distinct powder shifting from a dark brown to light gray as mineral decomposes. But look at the final slide highlighted in the golden frame at 1473. The powder has completely collapsed into a low melting point eutectic melt, adhering heavily to the surface. So thermodynamics tells us that any system spontaneously moves from a high energy state to low energy state. So here temperature is the driving force that forces this particle to release surface energy and sinter into dense impermeable mass. The operational impact is once you hit that 1473 Kelvin threshold, your loose ash becomes a dense plug that can no longer be carried out by the gas stream. So this transition from powder to plug is driven by a specific chemical interaction we call the sintering glue. So to manage slagging, uh, we have to stop thinking of ash as a single material. On the left, we have a component A, the solid brick. These are high melting point compounds like feldspar. So on the right, look at the amber glowing liquid component B, the glue. This is a complex, low melting point doped compound like calcium ferroalumina. So at 1473 Kelvin, this glue liquefies and mutually dissolve a brick, binding the entire system into dense, a smooth slag block as you see on the right. So what here is the key to our entire strategy. Slagging is not the melting of the entire ash the structure. It is a formation of this minority liquid phase that hijack the solid particles. So controlling slagging means starving the system of this liquid glue before it can bind your bricks together. So starving the glue requires us to track exactly when these mineral phases decompose and react. So let's look at the foundation of the reaction. So on the left, the SEM morphology at 873 Kelvin shows a loose, porous, flocculent structure. As fixed carbon oxidizes, it releases and leaving behind a massive specific surface area. On the right, the XRD chemical phase data shows us why at 873 Kelvin we have calcite, quartz and hematite. So by 1073 Kelvin, a massive decomposition occurs. Calcite breakdown into the uh, releasing breakdown, releasing more, which create the physical pores you see in the 1073 ACM image. This stage is critical because it begins reacting with the newly available to form calcium aluminate sulfate. So we are setting the stage here. This porous structure is actually good. It maintains gas permeability, but the chemical clock is ticking as the mineral become more reactive. As the temperature climb another 200 degrees, that porosity begins to vanish as atomic mobility takes over. So, uh, we enter the danger zone of a structural deformation, which is shown in the slide. So, look at the ACM image on the left. The flocculent structure have collapsed into distinct spherical particle to reach a stable thermodynamic state. So, you can see the point contact between the particle increasing, which indicate that the agglomeration has begun. On the right, the XRD data reveals the solid bricks of our model are forming. Highly active quartz is aggressively bonding with and to uh, form a feldspar. So the key status here, the ash remains fundamentally in a solid particle state. The so what factor? The foundation for the disaster is now set, but the destructive liquid phase is still dormant. If we find keep the chemistry in the feldspar heavy brick zone, we prevent the furnace from the choking. But if we lose control of the chemistry, we hit the 1473 Kelvin trigger point. So this is the point of no return. So look at the ACM. Uh, Look at the ACM image on the left. The surface is now flat, smooth, incredibly dense. The pores have vanished and the mineral particles are heavily sintered. The XRD data on the right shows the culprit. Anhydride has completely decomposed, flooding the system with. These react with and to form the highly complex structure, that is calcium ferroalumina. Because of the unstable iron and aluminum doping, this compound has an incredibly low melting point. It liquefies, dissolve your solid brick and bind the ash into slag. The operational impact is a total loss of permeability in the affected zone. We have moved from a gaseous environment to a liquid sealed environment, which is the precursor to a pressure spike. So to prevent this, we use thermodynamic modeling to visualize the liquid phase activation curve. So this graph is your most important diagnostic tool. The y-axis represents the mass of the liquid phase and the x-axis is the temperature. So notice the safe zone on the left where the ash is 100% solid. Then see the steep glowing red incline, the danger zone, where the liquid phase explode towards the 100. So to stop slagging, we cannot simply lower the furnace temperature that ruins your production rates. Instead, you must shift the activation curve to the right towards the hotter temperature by adding coal blend chemical composition. So using fact stage modeling, we have isolated the specific power of 4 core oxide to move this curve. So the what is that? By shifting this curve, we create a wider thermal safety window where you can run hot without melting your ash. The first variable we must control to shift this curve is the primary aggravator, silica. So the crystal and the delay mechanism. So let's look at the battle between the silica and alumina, silica and calcium. On the left, we have the catalyst. The SiO bond is necessarily a structural unit of low melting point compound. The data point is clear. If it exceeds 25%, liquid glue start forming as low as 873 Kelvin. These accelerate the entire slagging process. On the right, we have a delay. It's a double-edged sword while it promote coal combustion kinetics. See, it also raises the starting temperature of the liquid phase, pushing to 40% delay any liquid formation until 1373 Kelvin. However, once you breach 1473 Kelvin, higher calcium rapidly accelerate total liquid volume. So the operational rule is simple: minimize the silica strictly to prevent early melting and balance calcium carefully to exploit its delay without causing a liquid flood at peak heat. So while silica and calcium fight over the starting point, aluminium and iron determine how fast the system fails. So coming to our next slide about which is about the um, protector and the tipping point. Now we look at our protector and our wild card. Alumina is your most effective thermal buffer. Increasing beyond 15% successfully prevent the ash from the heating a 100% pure liquid state until temperature exceeds 1773 Kelvin. It expands the temperature range where the liquid formation is actively reduced. On the right, we have, so because Sendong coal is naturally high iron at nearly 23%, this is a volatile component. At 1473 Kelvin, 18% is the critical threshold. Keep it below 18% and liquid formation remains manageable. But once the furnace hit 1573 Kelvin, act as a rapid promoter of the liquid phase. The so what here is that alumina is your armor, but iron is the spark that can bypass that armor if temperature spike. So we can summarize all these thresholds into a single actionable operational impact matrix. And our next slide is going to share exactly on this topic. So this matrix is what you should print and keep in control room. It breaks down the role, the critical threshold and the operational rule for each oxide. So silica, so minimize strictly stay below 25% to avoid liquid glue at 873 Kelvin. Alumina maximize to protect stay above 15% to push the liquid state beyond 1773 Kelvin. So calcium balance carefully at the control around 40% to delay the internal melt. Iron keep below 18% to prevent the rapid catalyst for the a short of a glue. So the so-called factor is that there are not just numbers; they are your uh, uh, guardrails. So if your lab report shows that iron at 20% and silica at 26%, you are not just off spec, you are in an active slagging event. This matrix allows you to intervene before the 2 years start to plug. So this intervention works by physically re-architecting the ash at the molecular level. So coming to this slide, which is on uh, that is thinking of slagging as a controllable chemical equation. So as you can see, uh, on the left axis are pulling the system towards slag failure by fueling the creation of unstable glue, as you can see in the slide. So on the right, elevated and controlled are pulling the system towards solid oblique success by elevating the aluminum to silicon ratio. You force the calcium to bond into stable, high melting feldspar bricks rather than dissolving into the unstable glue. The so what is that the goal of blending is not to eliminate calcium, it is the manipulate the deposition form of calcium and silicon. So we are the effectively engineering out the slagging mechanism by architecting a more robust molecular structure that can withstand the heat and heat of the raceway. So we implement this architecture through the three-step strategic playbook for the furnace. So coming to our next slide about about a lot of thing on blast furnace. So to close, let's look at the three-step playbook for the utilizing high calcium coal without a slagging risk. So exploit the calcium delay, utilize high calcium coal for its superior combustion kinetics, but rely on to safely delays the initial liquid phase up to 1373 Kelvin. Second is dilute the aggravators. So blend with the coal specifically chosen to dilute total and keep iron strictly under 18% threshold. So in point number 3, armor with the alumina, where we introducing high alumina or blended coals to expand the thermal stability window. So pushing forces the ash to remain in a manageable semi-solid state all the way through the critical 1473 to 1673 Kelvin operating zone. So high calcium coal is not fundamentally flawed. By the architecting the ash composition, we can engineer out the slagging mechanism entirely. So thanking you for your time.